Hello, everyone. Today, I will present Dremel, adaptive configuration tuning of RocksDB key value store. I'm Chen-Xinyu Zhao. This is a joint work with Tapanchu, Qi Hongming, Arvind Krishnamurthy from University of Washington, and Ming Liu from University of Wisconsin-Madison. Currently, persistent key value stores are widely deployed. Diverse applications like database system, object storage, stream processing, and more. They integrate key value stores as a persistent storage layer. To serve applications, there are lots of systems implementing key value stores, including RocksDB, LevelDB, and so on. Among these systems, we investigate RocksDB. It's an industry standard implementation open source by Meta. Although key value stores are widely deployed, tuning key value stores to achieve high performance is not trivial. It has several challenges. First, the challenge is from massive configuration space. For RocksDB, it has tens of important nodes, as the example shows. What's worse, among these parameters, some have continuous range rather than discrete values. For example, buffer size can vary from kilobytes to megabytes. So the tuning space is huge. The second challenge is that there is fundamental performance trade-off between different types of operations. We did experiment here. We randomly sample hundreds of configurations to run RocksDB. This figure shows read and write latency. We can see that for some situations, one dimension cannot improve without hurting the other one. So tuning decisions have to navigate a good trade-off between read and write performance. At the same time, tuning system should filter out suboptimal configurations, which are not on the optimal curve. Third challenge is adapting to workload and hardware. RocksDB supports diverse workloads and hardware. It can be deployed over different storage media like SSD, HDD, or cloud environment. Also, it can serve workloads with different request types and with different read and write ratio. Here, we show an experiment. We set up 4 different scenarios, which include fast or slow SSD, read or write intensive workloads. We select 4 configurations to run over these 4 scenarios. We can find that no single config is always the best. So we should change configurations according to the specific workload and hardware setting. Different workloads and hardware further complicate configuration tuning. Fourth challenge for tuning is that testing configuration is expensive, especially in times of time cost. Generally, we need to replay trees for each configuration. RocksDB performance metrics converge slowly, as the figure shows. For each configuration, we need to wait for several minutes to query stable results. It's time-consuming to test the massive configuration space. So far, we have described 4 challenges. In this work, our goal is to address about 4 challenges. We hope quickly identify a configuration that achieves high performance while adapting to specific workload and hardware. Let's see how to achieve this. Before describing our solution, let's firstly review the underlying data structure of persistent key value stores. Most of persistent key value stores, like RocksDB, they use log structure merge tree as a basic data structure. Generally, LSM-tree consists of two major components, memory component and persistent storage component. Memory component organize data as memory tables to buffer recent updates, and memory component use a block cache to serve read request. Block cache is caching recently read blocks from the storage layer. Storage component organize data in access tables. Access tables are files of sorted key-value pairs. Access tables are structured in a series of levels, from lower level to high levels. LSM-tree supports read and write operations. For write requests, memory table firstly buffer the write request in memory. When memory table becomes full, it results in a store and cannot absorb new requests. To make empty room, recent requests are sorted as an access table and flushed out to storage. Access table is immutable. When lower level is full, compaction is to merge lower level access tables into higher levels. For read requests, data queries start from block cache. When a cache meets, it will look up multiple access tables in persistent storage. This is background knowledge for LSM-tree. Now, let's look at which key factors will affect read and write performance. Because configuration tuning essentially is to play with these performance factors. As the structure shows, LSM-tree is split into two components. Read and write are two main types of operations. For write, key factor in memory component is write buffer, and key factor in storage component is compaction. For read request, key factor in memory component is block cache. And in storage component, read accessible cost affects read request a lot. Here, we have an important observation. Abstract factors are fewer than tens of configuration parameters, which motivate our following ideas. Given that abstract performance factors are fewer than raw parameters, our first key idea is to feature fusion, which is to handle massive configuration space. Our insight is we can fuse a large number of original parameters into a small number of fused features. Then we can tune configuration over fused features rather than raw parameters. Specifically, we propose 4 fused features corresponding to key factors affecting the performance. For write, we have compaction frequency and write buffer full frequency. For read, we have read accessible cost and block cache hit rate. After identifying these features, next step is to combine raw parameters into fused features. To achieve this goal, we hope use closed form expressions to map raw parameters to fused features. Question for now is that how to derive closed form expressions? We use domain knowledge to derive closed form expressions. For example, for compaction frequency, we conduct asymptotic worst case analysis to get this term. Please check more details in our paper to understand how to derive this term. By translate this term to RocksDB parameters, we can obtain unclassifiable expression. By this expression, we can combine several parameters into one fused feature. Then tuning space is reduced. Holding 4 fused features, we can represent configurations with fused features instead of original parameters. Now each configuration has 4 feature values. We group configurations which have the same feature values. After generating representation for configuration, we will start to answer the following question. Which configuration is the best for specific workload and hardware? To adapt to different workload and hardware, we use online tuning method. For such setting, Bandit-based model is suitable. We use multi-armed Bandit to model our process of identifying which configuration is good. For multi-armed Bandit, there are several key concepts. First one is arm. In our setting, each arm is a group of configurations which have the same feature values. The second concept is arm pooling. In our setting, pooling the arm means sampling configuration from arm to run and collect metrics. Common to other Bandit problem, we have to figure out which arm is the best. In other words, which configuration is the best for RocksDB. Also, we need to answer how to quickly identify the best arm. To identify the best arm, that is the best configuration, a simple method is to run the entire workload for each configuration. Each configuration is sampled from each arm. However, it is expensive in terms of time cost. Instead, we take an approximation strategy called as successive halving. Instead of running the entire workload for each configuration, we can perform an early stop for the worst half configurations. For example, as left figure shows, at 60 seconds, we stop the worst half. At 80 seconds, we stop the worst half again. We conduct 3 rounds of halving in the experiment. By doing this, we can reduce the cost in total. Now, after describing our 3 key ideas, feature fusion, Bandit-based online tuning, and approximated quick evaluation, we can integrate them as Dremel system to tune RocksDB. By this workflow, from massive parameter space, we can identify a configuration which can achieve high performance while adapting to specific workload and hardware. Next, let's talk about our evaluation results. We set up different workloads and hardware to test if Dremel can be adaptive to different settings. We use synthetic and real workload, also varying the read and write ratio. To simulate different hardware conditions, we rate limit SSD bandwidth. We simulate 2 adaptive scenarios. One is the initial config, which doesn't have preloading data. Also, we simulate adapt on the fly scenario, which has preloading data. Dremel can be used to optimize lots of metrics. In our evaluation, we show the results for IOPS and latency. In this experiment, we compare Dremel against Bayesian optimization methods, random search, and expert experience. Here, expert experience is from the official RocksDB tuning guide. That configurations are based on the best practice advocated by RocksDB. With the same tuning time, Dremel finds configurations that can achieve higher IOPS. From figures, we can see for 6 settings, Dremel can find configurations achieve better IOPS. In this experiment, we show the time efficiency of Dremel. We vary the time budget for Dremel to find configurations. We can see that Dremel finds better configurations faster. Different from others, we can notice that Dremel requires minimum time budget. It is because Dremel needs pulling each arm once before making decisions. So Dremel will require a minimum time budget. When Dremel has more time budget, it can pull each arm multiple times. It can find better configurations. This shows the flexibility of Dremel on the different time budgets. Besides IOPS, Dremel can optimize other metrics. Example, reducing the latency. Also, we break down the whole system and evaluate every components like feature fusion part, approximated evaluation part, and so on. We also discuss how to use Dremel to tune other storage systems. Please check more details in our paper. In summary, we investigate 4 challenges when tuning key-value stores, including massive parameter space, inherent trade-offs, diverse workload and hardware, and expensive evaluation. To address these challenges, we design and implement a tuning system, Dremel. It can quickly identify the configuration that achieve high performance while adapting to specific workload and hardware conditions. Evaluation results show that Dremel can achieve better end-to-end performance with less tuning time and more flexibility. That's all. Thanks for listening. I'm happy to take questions.